This is our presentation, Gravitational Interactions by Milo and Van.
What is a gravitational field?
A gravitational field is a kind of area that surrounds objects with mass exerting gravitational force on any other mass. On the surface of a planet, it can be found G equals gravitational constant times mass over radius squared. It is measured in newtons per kilogram. At any point, it can be found with G equals gravitational constant times mass over distance between their centers of mass squared, following the inverse square law.
This means that if the distance is doubled, the gravity is 1/4 as effective. Gravitational fields can also be represented with field lines. They point in the direction of gravity and show that gravity is stronger where they are closer together.
To represent the relationship of gravitational interactions, we chose TON 618, a supermassive black hole, and Halley's Comet, which passes Earth every 72 to 80 years.
TON 618 has a mass of 66 billion solar masses, or approximately 1.3 times 10 to the 41 kilograms. Halley's Comet has a mass of approximately 2.2 times 10 to the 14th kilograms. Since they are so far away, we will be representing their distance with 1 light year, or 9.5 times 10 to the 15th meters.
First, we must find the gravitational field of TON 618 in Halley's Comet. We'll start with TON 618. G equals 6.67 times 10 to the negative 11th times 1.3 times 10 to the 41st over 6.5 times 10 to the 15th squared. When you run those numbers, the gravitational field strength of TON 618 at 1 light year away is 0.096 newtons over kilograms.
Now, for Halley's Comet. G equals 6.67 times 10 to the negative 11th times 2.2 times 10 to the 14th divided by 9.5 times 10 to the 15th squared. This results in a gravitational field strength of 1.63 times 10 to the negative 28th Newton kilograms at 1 light year away.
What happens when these forces actually interact? To find force, we'll look at how TON 618 affects the comet's mass with Newton's second law, force equals mass times acceleration. So, F equals 2.2 times 10 to the 14th kilogram times 0.096 newtons over kilogram. Therefore, at a distance of 1 light year, Halley's Comet is pulled into TON 618 with approximately 2.11 times 10 to the 13th newtons of force.
And because acceleration equals force divided by mass, the comet's acceleration towards TON 618 is the same as the field strength, 0.096 meters per second squared. We can use the formula v orbit equals square root g times m divided by their distance between their centers of mass to find the tangential velocity necessary for Halley's Comet to maintain an orbit of TON 618 at a 1 light year distance. V orbit equals square root 6.67 times 10 to the negative 11th times 1.3 times 10 to the 41 divided by 9.5 times 10 to the 15th. This comes out to be 30,200,000 meters per second, which is the tangential velocity Halley's Comet needs to have to orbit TON 618 at 1 light year away.
We can also find the Reusch limit, the point at which the tidal effects of a large mass on a smaller one becomes powerful enough to overcome the smaller mass internal gravity that it tears apart. So, D, or Reusch limit, equals r, the average radius of Halley's Comet times the cube root of 2 times the mass of TON 618 divided by the mass of Halley's Comet. D equals 5,500 times cube root 2 times 1.3 times 10 to the 41st over 2.2 times 10 to the 14th, resulting in a Reusch limit of 5.8 billion kilometers. Once Halley's Comet passes this line, TON 618's gravity will tear it apart.
With this, we should also find the orbital escape velocity at 1 light year away. V equals square root of 2 times gravitational constant times the mass of ton 618 divided by the distance between their centers of mass. Therefore, the necessary escape velocity is approximately 42 million meters per second to escape ton 618's gravity. That's over 14% the speed of light.
Lastly, we'll find the tidal force at 1 light year away. F equals 2 gravitational constant times mass of ton 618 times mass of Halley's Comet times the length of Halley's Comet divided by the distance cubed. This comes out to be 66.8 newtons. At the Royce limit, the tidal force explodes to approximately 291 billion newtons.
While Halley's Comet and ton 618 are extremely far away from each other, these equations demonstrate the influence that gravity has on all masses throughout the universe.